All right, thank you for coming today. Standing room only for me, it looks like. It's my pleasure to introduce Dr. Brent Delbridge. Brent grew up with Mount St. Helens in his backyard, pretty much. He went to the University of Washington, where he double majored in physics and computational mathematics. And I say that to the undergraduates here. The reason he is here today is because he got involved in research as an undergraduate and then went to Cal Berkeley for his PhD, where he worked on fault mechanisms. And after Berkeley, he moved to Harvard, where he was a postdoctoral researcher and is now at Los Alamos National Labs. Somewhere in all of that time, he taught English in Beijing and also Sendai as well. So without any further ado, I'm going to hand it over to Brent.
Thank you very much. All right. So I've lived several different lives, but today I'm going to tell you a little bit about the lithosphere and what I think the deformation and strength of it is and what we can learn about it from seismology. So this is Roland Bergman was my PhD advisor at Berkeley. Heidi Houston was actually used to be at University of Washington, and she's actually the one who got me involved in earth science research and converted me from pure physics to geophysics. And so this research builds upon stuff I've been doing since the very beginning of my entry into Earth research. Saiko Kida and Yoichi Asano, I actually met when I was working in Japan for a short period of time through the NSF program. Okay, so primarily my work uses seismic waves to understand seismic sources and what those seismic sources can tell us about the structure and dynamics of the Earth. And what our understanding of both the structure and the mechanisms and how we can mitigate those hazards. But today, I'm going to focus more on what we've learned about our understanding of the interior of the Earth and how it deforms, rather than the mechanisms that generate the seismic waves. If you're interested about seismic source, that's primarily what I work on now at Los Alamos, and I'm happy to chat about that at any time. The question that focuses a lot of my research is basically trying to understand how the energy transfer has shaped the modern Earth that we see today. So in my view, every geologic process involves the transfer or exchange of energy from one form or another. And my work has been largely focused on trying to understand various different aspects of this energy transfer. For example, at the surface of the Earth, and importantly at the core mantle boundary, we have the exchange of heat from one body to another, and we have mechanical energy, which drive the convective motions both in the mantle and the outer core of the Earth. And importantly, for the outer core, those convective motions are actually what generate the magnetic field. So looking at the heat, I've tried to understand how much heat is leaving the Earth through submarine volcanism by trying to increase our ability to detect submarine eruptions. Looking at mechanical energy, while storage strain energy in faults is not actually a large part of the Earth's overall energy budget, we actually do care about it because it causes earthquakes and we live on the surface of the Earth. So this work is primarily focused on trying to understand how the faults, on this in particular, these two studies are looking at the San Andreas Fault near the Parkfield region. And then those works are trying to look at how can we use seismic waves traveling through those faults to understand how the mechanics of that fault is changing over time, and how can we use that to lower the hazard posed by the shaking of those events. Other things I've looked at is trying to use large, slow-moving earthquakes as analogs for basically large-scale experiments to look at the mechanics of faulting. And in those methods, we're primarily using and developing new geodetic techniques from both spaceborne and uninhabited area vehicle synthetic aperture radar, which is basically a drone that flies and uses radar to map how the surface of the Earth is deforming through repeat pass. The funny thing about this was I spent some time at the JPL as well working on this. That uninhabited vehicle typically was actually like a Learjet with 11 people on it. But that's okay, we kept the name. And what I'm going to try to focus a little bit more on today is understanding the subduction zones. Subduction zones are where the cooling of the oceanic plates, as they get heavier and heavier, sink into the mantle, and actually that gravitational energy provides the energy to drive convective motions in the Earth. And so what we're going to try to understand today is a little about that process and whether or not this is actually going to be an important key driver in understanding our larger scale mantle motions. And as an aside, one of the reasons we really care about the mantle convection over time is if we want to run this machine backwards through time, this is what's going to control the heat flux out of the core mantle boundary. And the core mantle boundary heat flux is one of the key drivers which drives motions in the outer core, which drives the Earth's magnetic field, which is important for everything from habitability to being able to have DNA life without cancer, and electronics that still function. And as I'm giving this on a computer, we all are hopeful that our electronics continue working. But the focus of this talk, which I'm going to talk to you for the next, I guess, I don't know if we're on a strict time schedule, but now 30 minutes or so, is I'm going to talk to you about how the rheology of the subducting plate, so in this little cartoon, this is the continental lithosphere, and this is the subducting oceanic lithosphere. How does the rheology of this plate affect the overall mantle convection? And the way we're going to do that is we're going to use seismology to try to answer the question of how strong is this plate as it subducts? And is that an important factor that we need to consider in this larger system? So, well, we're going to start at the very beginning. So we have the oceanic lithosphere. As we go from the top of the plate down through the plate, we have pressure increasing. And this is just the density of the Earth times gravity, right? So this is just lithostatic pressure. And the temperature goes from the temperature at the top of the plate to something that's in the temperature at the bottom of the mantle. And what we're going to see is that how the lithosphere accommodates deformation in these two regions is a little bit different, and it's dependent on the pressure and temperature. So in the top of the plate, where it's cold and at relatively low pressures, where the deformation is accommodated through brittle failure. And this is shown by the peanut brittle. The idea is that as you bend it, it'll be elastic until it reaches some pressure and then breaks. And the way that this has been looked at is maybe we're going to assume that there's broken pieces in all different orientations already, and that's largely where you'll get earthquakes. On the bottom, as it gets hotter and it gets more pressure, we no longer get brittle failure, we get ductile flow. So if we just stick our silly putty at the top here, eventually, if we wait long enough, that silly putty is just going to flow. And so we're going to use these mechanisms, and we're going to interrogate them a little bit further. So in this upper region where it's cold, the sort of more quantitative law we use is something called Byerlee's law. And there we're showing that the maximum shear stress, so on the x-axis we have the normal stress, on the top we have shear stress. So if you imagine two blocks, I'm squeezing them together. How hard I'm squeezing them together is the normal stress, and then I'm pushing them in different directions. How hard I'm pushing them is the shear stress. And experiments have shown us that as I increase the normal stress, the stress at which that block moves or the rock breaks increases linearly. The normal stress in the Earth is provided by the overburden pressure. So as we go further into the Earth, the shear stress which is required to break that rock increases linearly. And this is all from experiments and been confirmed. It's not dependent on temperature, it's not dependent on rock type. This is a pretty universal relationship, and that's not something theoretically that should make sense, but it's something that's shown very experimentally to be very true. For the lower part, because it's hot and because the normal stresses get so high that it's hard to actually break the rock brittly, before the stresses have a chance to get high enough, this will actually flow and release those stresses. And so we can do experiments to look at this kind of behavior as well. And those experiments have shown that this mechanism is temperature dependent. So if you increase the heat, it'll flow easier. It is not dependent on pressure. So if you increase the pressure, it doesn't care. Okay? And I'm showing this now because I will use it again later. This is just the strain rate. So it's how fast it's being deformed over the viscosity. This is a stress factor that's related to the differential stress, which is basically the largest shear stress I put on there. And this is something called the deviatoric stress, which is the stress that's not due to pressure. Okay, so we can put these two things together. So up top, so here we're looking at depth along our oceanic plate. We're taking our assumed pressure, some modeled temperature. You can model the temperature however you like. Here we're doing something quite simple. We're just saying that at a location of the thermal boundary layer, it's equilibrated to about 90% of the mantle temperature. Combine these two, and you can build this thing we call a yield stress envelope, which is the maximum stress that the plate should experience at that depth before it breaks. Below that stress, we can consider it to be elastic. So if I put at 20 kilometers depth, I put 200 MPa of differential stress, that will still be elastic. If I increase that to, say, 500, that's going to break. And down here, I'm showing that it'll flow. Now, I've kind of hidden one other piece in here in this calculation, which is that I've assumed a strain rate. And that strain rate for this calculation is actually calculated from the plate rate and the curvature of the plate. And we'll talk about that a little bit more later. And you'll notice if you know about the rheology of materials, you'll notice there's like a slight difference here. That's because they're two slightly different mechanisms of deformation that cause that. So for ductile deformation, you can kind of think of it as a lattice of atoms, and there are a couple gaps, and you're kind of reshuffling those atoms as you're moving those gaps around. And there's two different mechanisms dependent on temperature that cause slight differences. But if we plug this into a power law, as I showed at the very beginning, the sort of viscosity we get is something that's about on the order of 5 times 10 to the 22 pascals per second. And this is something that's sort of commonly used in a lot of mantle and plate tectonics. So all of those plots were I've shown you for the oceanic lithosphere, but now we're bending the lithosphere. So what that creates as I bend the lithosphere is if I take my plate and I bend it, the top of the plate now has to be longer, right? So I'm traveling further. So I'm extending the top of the plate and I'm compressing the bottom of the plate. And so schematically we're showing that as we move from the center about where it's bending, I'm moving further away from the center, and I have cars more extension and more compression. Where that value exceeds the yield stress curve, we're just on that curve. Below that, we're at elastic values. So what's important here is that if we actually try to use this model to look at subduction zones such as Japan, these elastic stresses quickly exceed all of this, and we're basically just the strength of the slab is just the strength of this yield stress curve. One other thing I want to mention here really quick that I remembered that is in my notes that I can't see. From observations of topography on the Earth, we know that the strength and the sort of differential stresses that are required to be in the lithosphere to maintain something like a mountain, because you can imagine if you put a mountain and just float out, there would be no mountains. So we have to maintain some amount of horizontal versus vertical stress. And what those are estimated from topography are on the order of 100 to 300 megapascals. We can do the same thing if we try to predict this outer rise curvature, and again we get about a similar answer. However, if we look at what happens when the lithosphere actually breaks during an earthquake, we actually get estimates that the amount of stress released is only on the order of several megapascals. And if we look at gravity measurements along about the trench here, we can show that this elastic thickness is 0 past the trench. And I'm going to argue that I'm going to argue in this talk that actually down here we also show that the plate is very weak and only accommodates stress on the order of several megapascals. So we've sort of got this problem now where topography is saying that the lithosphere is really strong, but earthquake observations and gravity observations are saying that the lithosphere is very weak. How are we going to do this? I'm going to try to do this through observations. Everything I've shown you before is from laboratory models and geophysical models. So what we're going to do is we're going to determine a really precise catalog of earthquake focal mechanisms within the subducting slab. And then we're going to do something, a sort of complicated inversion, which I'm not going to get into the details of, and we're going to combine those focal mechanisms to infer what we think the background stress within the slab is. And we're going to do that as a function of time before and after a really large earthquake. And then we're going to combine this to estimate what we think the actual state of stress in the lithosphere is. And we're going to do this in two different ways. One is I showed at the beginning that sort of hinge point where we were bending, where the top part was extending and the bottom part was compressing. We're going to show that during this earthquake that actually moves, and we're going to use that to estimate what we think the rheology of the plate is. And we're also going to use a second sort of independent method where we combine our orientations of the principal axis before and after the earthquake, combined with a sort of model of this large earthquake to then also invert for what we think the actual deviatoric stress levels in the slab are or were. And the punchline, which I already kind of gave away, is that the answer we get using both of our methods is that the slab is very weak. On the order of less than 2 megapascals, amount of shear stress is being stored in the slab. I'm going to show this figure a fair amount just to kind of help keep everyone oriented. And what we have here is we have the subducting Pacific plate. You kind of imagine up here is the mainland of Honshu in Japan. U we're going to use for the plate rate, so that's how fast the oceanic plate is subducting below. That's on the order of like 10 centimeters per year. As the plate bends, it has to change shape because it was straight. and now it's bending, and then it's straight again. And the sort of delta U, delta Y we're showing here is accommodating that shape change. That's actually a function of time. What we're showing here in the red and blue vectors is what we're going to call sigma 1 and sigma 3. But I think intuitively, the way you should think about them is the red one is the direction where it's being squeezed the most, right? So that's the direction of being squeezed, compression. The blue is the least compressive direction. I might call it the tensile stress, but that's only in the world where we've removed all of the overpressure, because at these depths, everything is being squeezed because we're at 70 kilometers depth. But this is the direction in which it's being squeezed the least. X is going to be my distance down the plate, and Y is going to be my distance from the top of the plate to the bottom of the plate. And for plate bending, we know what we should expect is in the top, the most compressive direction should be a line down dip, and underneath, the most compressive direction is perpendicular, or the least compressive direction is a line down dip. And we'll come back to the plunge, but if you're a geologist, you're well aware of plunges, but for the rest of us, a plunge is basically, if you have the horizontal, it's the direction relative to the horizontal, so it's how steep you are relative to horizontal. Okay, step one. First, we're going to look at the Tohoku earthquake. So this happened in 2011. It was the largest recorded earthquake in modern history. And the reason this is such a great opportunity for us to study this is each one of these kind of colored triangles. So the colors on this plot are showing the intensity of shaking from the earthquake. But all the triangles on top of there, those are each seismic stations. So this is an incredibly well instrumented area, and it's next to the largest earthquake ever recorded. So this is giving us a really unique opportunity to study what's going on deep in the slab. As a sort of fun aside, when this earthquake happened, I was still a physicist, and I was working in an atomic physics lab in the University of Washington in Seattle called the Center for Experimental Nuclear Physics and Astrophysics. And so I was, so they have the undergrads doing research, and for some reason we get to run the shifts from like 10 p.m. to like 5 in the morning. That's, yeah. But we were measuring and we saw this weird spike. And this is, I think, around like 318. And this is these are measurements from a scintillator measuring gamma ray. And so I think that's like iodine 131. And this peak started happening about 5 days after the earthquake and got really large, 10 days. And what we're actually seeing here is the results of the Fukushima nuclear reactor disaster that came because the tsunami from that earthquake came up and damaged the reactor. And so this is actually radioactive material traveling through the atmosphere all the way to Seattle. So this earthquake, even before I was studying earthquakes, was affecting my life. Okay. Returning back to the seismology of the earthquake, what we're showing here again is a map view. The sort of gray to black areas are the amount of slip that occurred during the earthquake. So slip during an earthquake for a subduction zone, right? We're taking the overriding plate, a sinking subducting plate. The yellow star is where we're going to center our transect, and we're going to take a transect down dip, and then we're going to collapse everything onto that transect. And that's what we're plotting here. The gray dots are focal mechanisms that we determined for use in this study, where I've colored the ones in the upper plane. We'll show you how we determined the upper plane and lower plane later, but by purple and the lower plane by green. Notice that we're only looking below 70 kilometers. And this is, distance along the transect is in this direction. We're only looking below 70 kilometers, and at this depth, we don't expect there to be any earthquakes on the plate interface because the pressure is too high. And instead what we see is these two bands of seismicity below the plate interface. And the plate interface is sort of this dashed line shown above. It looks like dots are at the plate interface or above, but that's actually because I've taken a transect and collapsed it in 2D. They're actually all below the plate interface. And for what's the word I'm trying to say? For comparison, the sort of black circles here with the white dots, that's the previous existing catalog before this work. So that's the catalog that's been determined routinely by something called the F network in Japan, which is a network of broadband seismometers. And so what we're able to do is determine these focal mechanisms of the green dots in a really high precision. And so we can actually go to much lower magnitudes. And so that greatly increases the number of events we have. And so we can do a lot more statistically robust examination of this deeper portion. And so that's one of the large motivators for why we're looking at this deeper depth. Because to get a focal mechanism, you need observations in all azimuths. So a focal mechanism is kind of a weird seismology plotting technique where you're showing the orientation of slip on the fault relative from the top. So I've kind of done something bad here where I've taken a focal mechanism plotted from the top on the side. I apologize. But you can imagine the event is right here in the middle. And if you are directly above the event, you'd plot your observation here. If you're far away from the event, you're over here. This is north. This is east. This is south, west. Okay? So the reason these intermediate depth earthquakes are so powerful in this study is because all of our stations are above the events. So we have observations in every azimuth. If we go further offshore, all of our stations, and so we're only looking in one direction. And so you can see for some of these events, maybe we don't have any observations over here. Okay, now what we're going to do is we're going to take all of those, so you can imagine like a fault slipping, and that's what we get from the focal mechanism. Now we're going to combine all of those faults and back out what we think the background stress in the rock hosting all of those earthquakes was. Okay, so again, just for reference, what that gives us is not the full stress tensor, but just the orientation. So what we get from this inversion is the orientation of this red arrow and the blue arrow, right? So we get the orientation of the most compressive direction, the least compressive direction. I've shown, but because it's boring, I'm not going to really talk about it because it's all in and out of the board. That's the intermediate one. And it kind of behaves as we'd expect and never really deviates. Sigma 1 in the upper plane, again, is the angle here relative to horizontal. Sigma 3, relative horizontal, upper plane, lower plane. Okay, so now what we're going to do is we're going to look this as a function of space. So we're going to take bins about 7 kilometers wide and move them down through the slab. Okay, and then what we're going to do in this plot, this is depth and this is plunge. So we're just going to plot the plunge of these vectors which we get from our inversions as a function of distance from the top of the plate. This black line is the sort of dip or plunge of the dip of the plate interface, and that's the vertical black line. So what we see as we go from the top of the plate at the beginning is the red arrow is perfectly aligned with the plate interface, right? So we get about 25, 28 degrees. As we keep going, though, at some point, the sigma 3 switches, and sigma 3 is now aligned with the plate interface. That's how we determine the location of the neutral plane. Right? So this is the place where if you expected that you were bending the plate, the top of the plate is being extended, bottom of the plate is being compressed. Here's where it occurs according to our earthquakes. Now, all of these calculations were done before the magnitude 9 earthquake. We do the same technique after the earthquake, and what we see is that there's some deviation. The sigma 1, again, this arrow is almost aligned against the plate interface, and then at some point it switches and sigma 3 does. The only difference here is the location of that neutral plane is shifted by about 5 kilometers. So what that means is that this plane moved down 5 kilometers. And these are very precisely relocated earthquakes. And this is not occurring because all the earthquakes are shifting in location. This is occurring because the actual stress tensor or the inferred stresses are shifting, not the earthquakes themselves. If you want to know more details about this, actually this paper came out Friday, like what day is today, Tuesday? 4 days ago or something. So it's available, you can read it. So if we take now we're going to look just right here in those events, to look more carefully what we actually are inverting, because I want to explain to you it, if you don't know what a stereo net is, similar to the lower hemisphere projection we showed for the focal mechanisms. What you have here again is straight down is right here, horizontal is out here, and azimuth as you move around clockwise. Okay, so this line is, anything on this line is basically in our 2D transect here. And what I'm showing by this black star is that's the dip of the plate interface. And from our inversion, that's the sort of vector we plotted. So what you can see is that before the magnitude 9 earthquake, this area was an extension because the extension was aligned with the plate interface. After the earthquake, compression was basically aligned. So this region right here switched from extension to compression. Okay, so now what we're going to try to do is use that observation to learn about the rheology of the lithosphere. Okay, again, this is our observation, and we're looking in this region. But we're kind of tilted, right? So one thing to note that might be confusing is that this is not depth, right? So this is not depth this way, it's depth this way along the y-hat direction. And that's the sort of shifted coordinate system we're going to work in for a few minutes. How can we sort of understand this shift? So let's go back to what we think the background stress state was. So we're going to represent the neutral plane by this red line and this sort of cartoon drawing of extension. We've sort of switched here. So this is compression over here and less compression this way, right? So we have compression increasing and decreasing and then less compression. We can superimpose on top of that what we model as like static stress from the magnitude 9 main shock. And so sort of in the cartoon land, if you think about the subducting plate shifting, what we've done is compressed the plate. So almost the entire section of the plate has been compressed. So we've sort of shown here is increased compression across the entire plate. Now this is slightly sloped because the magnitude of that compression is a function of distance, and the bottom of the plate is further from the top of the plate, which is where the earthquake is occurring. So if you can kind of think of putting this line, adding this to it, And so you can see the dashed line here is where it was, shifting it over. And now examining where that shift happens, it's down here. That's the sort of cartoon way of thinking about why, when you add down dip compression from a large earthquake to something that was previously the stress state was bending, why it would cause the neutral plane to shift. Cartoons are really great, but we can't actually use them to do anything quantitative. So what we're going to try to do here really briefly is walk through how we've sort of derived an expression that will relate the shift in location of the neutral plane to the rheology of the plate. So what we do is we take so previously this was a tensor, which is like a matrix that describes how the stress and strain in all directions in any orientation are described, but now we're just looking at just the down dip strain in the down dip direction. And so that's a function of y. So this sort of gets you that linear piece, and that's the distance from the neutral plane. U, which is again is the plate rate. K is the curvature. So that's how fast you're changing the shape of the plate and how fast that curvature is changing. So this is just a kinematic. So this is kind of, think of this as like a geometry, right? So this is saying, how do I have to deform this chunk of plate for it to have this shape as it goes down and subducts into the atmosphere, the mantle. Okay. This is sort of the general expression we showed previously, which is an expression for how we can treat the flow. This is a rheological parameter, and this is related to the differential stress. This rheology parameter, you can kind of think of this as the long-term control geologic curvature. So like on time scales of like 10,000 years, how strong is the plate? And that's what this sort of parameter is. If you put n equals 1 here, this just becomes regular viscosity. Okay? Combine these together, now we can relate the stress to our strain, and we can plug in our expression for the strain. And so this guy right here is in that, if we think about our cartoon, this is sort of the slope of that line we were plotting. This is where we're plugging that into that expression. For simplicity, I'm going to show here the case for n equals 1. And that's the sort of, we're saying that this plate is actually just regular Newtonian viscous material. If we do that, we can put our down dip stress change is linear related to our viscosity, plug in for our strain rate, plug in the expression we derived before. The one thing we're going to do here is we're going to change the delta K delta X, which is how fast the curvature is changing here. And what's commonly used in literature is something called the radius of curvature. And so we're just going to plug in that value. But kind of the way you can intuitively think about that is if I take a plate and I bend it, if I try to draw a circle in that little bending area, what's the radius of that entire circle? So as it bends really fast, that circle gets really small. As it bends really slow, that circle is big. Okay? So for Japan, we're just going to plug in that value. And this is the observed change in neutral plane, which we calculated earlier. And this is something we can observe at the seafloor. And what we're going to calculate is this eta right here. This is coming from the stress change of the magnitude 9 earthquake, which we're calculating. Okay. So the stress change at this depth is about 0.5 megapascal of compression across the entire plate. The change in the neutral plane we observed was 4 to 5 kilometers. Plug in these other values from literature. What we get is an eta around 10 to the 15 to 10 to the 16 pascals per second. This is about 6 orders of magnitude smaller than what we calculated at the very beginning. If we play the same game and calculate what our effective eta, plugging into the same expression, is using these laboratory laws, we get 10 to the 22. So what this means is that something in our modeling is incorrect, right? We need some mechanism that's rapidly weakening the plate as it goes through the trench. And so either you have something which drastically reduces Byerlee's law, or somehow maybe you have some kind of heating that causes more heat, and so our thermal ideas of how thermal model this lab are wrong. But the point is we need some kind of strong weakening mechanism to make our observations match what we think the plate is happening with the plate. Okay, so next what we're going to do is we're going to double check this observation using an independent method for what we think the actual deviatoric stress is in that region. So this is what we're going to do in this case, is rather than look at 7-kilometer slices, since down here sigma 1 was about constant and the same, we're going to lump them all into one bin. And the same with the lower planes, we're going to lump those into one bin. And so we have, that's, I don't go to 0 here, just for record, because just in case there are any plate interface events that somehow maybe, because there has been evidence to have shown that following large earthquakes, there can be a deepening of events on the plate interface. So we're going to avoid that, so we'll just throw away the first 7 kilometers. There's like 4 events in there, so we haven't really thrown away any earthquakes. So this is the upper plane, this is the lower plane, before the earthquake, after the earthquake. We see about a 20-degree shift in sigma 1. So what's happening there is sigma 1's was down here, down the plate interface, and now it's a little bit shallower. And then we see a similar but smaller shift in sigma 3 in the lower plane. So what we're going to do is we're going to do a quick inversion. We're going to input our observations. This is just, I'm showing examples for the upper plane. And what we're going to do is we're going to plug in we know the orientations of the stress tensor. We just don't know the exact scalar values. And same, so we know them before and after. But what we do know is we can calculate the shear stress change we expect from the magnitude 9 earthquake. So this is another reason that we're more interested in the intermediate depth earthquakes rather than shallowly, because we're looking down here. The magnitude 9 earthquake is occurring over here. The sort of details of different slip mechanisms are not going to be we're not going to be as sensitive to them a couple 100 kilometers away. This term right here is just a term that sort of lumps together all of our uncertainty. And so we know that we're not modeling our stress change from that magnitude 9 earthquake perfectly. So there's some error there. I also know that there's some error and scatter here, and it's probably not perfect. But we're going to try to assume that those errors are Gaussian and then invert for that. Just as an aside really quickly, how do we actually calculate the stress change from that magnitude 9 earthquake? What we did is I showed that sort of 2D histogram in gray at the very beginning. What I do is I discretize that. Each of them is a little patch that's moved, and then I sum them all up, and then I calculate the stress tensor everywhere. What that allows us to do is that actually gives us a stress change tensor like these guys. However, what we don't have for the earthquakes is we don't actually have the corresponding principal values, like how much compression is in the most compressive direction and how much compression is in its least compressive direction. So in terms of mathematically, you can think of these as the eigenvectors and eigenvalues. And sort of we have Our original inversion had 4 parameters, but the stress tensor has 6, so you can kind of think of these are the 2 parameters that we couldn't constrain from our stress inversions, if you understand that. If not, it's a detail that you can just trust me. So this is sort of the results of that inversion. What we have here is, on this x-axis, is C before and C after. And so we have a kind of misfit space it's kind of broad, but what I'm going to show in the next plot is even if you choose any of these areas, it's not going to change our conclusion. Okay, so using our calculated C before and our S again, which is our orientation of the stress tensor, we can calculate the maximum shear stress before and after in the upper and lower plane. So this is that tau value before. This is the tau, this is before, this is after. Again, we have the kind of blue and brown to try to help us. And what I'm plotting here 7 dots because seismologists have lots of opinions, and many different groups estimated different slip distributions as inputs into here. So what I've done is went and took all of them, and for each of them I redid this calculation. So each one of these dots is a different model for slip distribution. The sort of ugly circles here are sort of rough estimates of our error from our misfit surface. But what the key takeaway from this plot is that even if you went out to here and said, okay, actually my solution's in this weird part of my solution space for this one event, one slip distribution, we're still only getting answers of 3 to 4 megapascals of stress in the slab. A more intuitive way of thinking about it is that when I had sigma 1 and what we observed is it was pointed this way and now it's moved this way. If I put a weak perturbation on that and this is really strong, this orientation is not going to change. If I put a weak perturbation on that and it's weak, it will change. And what we observe is that if you're going to move it that much, the background stresses have to be low. And so intuitively it makes a lot of sense, but this is just how you would calculate that quantitatively. Okay, so what we're going to try to do one last thing is try to interpret this a little bit in terms of mechanics of what the faults that are experiencing this stress change are doing. This is shear stress, this is normal stress. So this radius here is something you would call that's about the magnitude of the shear stress. This point here is the normal stress. So that's the applied normal stress in that region. So if you increase the normal stress, you're going this way. If you decrease the normal stress, you're going this way. This is that Byerlee failure line. Okay, so the idea being for any okay, this gray line here is the normal stress on that fault, right, is dependent on how that fault is oriented, right? So if I change this, it'll change the amount of clamping I have on that fault. This gray line is saying, well, let's ignore that and say, let's look at all orientations. And this point right here is the optimal orientation in which you would first fail. So as you decrease normal stress, you hit this failure line, and now that rock breaks. I'm going to do a cruel thing to you because this is the way rock mechanics look at it. I flip it because mathematically this is the correct way, but people who like to compress rocks refuse to plot it this way. But I'm not going to let them win. Sorry. Okay, so what we're looking at here is the same plots as we've done before, but that inversion, I don't know actually anything about the normal stress. So if I think about this red circle, which is the upper plane before the main shock, I don't actually know where it is on this x-axis. Okay? So I'm just going to try to see what happens if I shift it and say now I'm going to shift it to the right normal stress so that it just fails. And I'm going to do that for both before and after the main shock in both the upper and lower plane. No matter what you do, no matter what value of this failure line you pick, the only way you can get these earthquakes to fail is if the pore pressure is almost above like 98%. So that's saying if you want these earthquakes and these background stress states to be working the way, like with more Coulomb failure, the way we learn in textbooks, the only way you can do that is if the pore fluid pressure is at lithostatic pressures in the plate. And that, at least in the upper plane, would give you enough weakening to match our observations. But even if you, okay, so the idea of here being that is if you actually reduce the friction values, no matter how low you increase them, you have to have near lithostatic pore fluid pressure. Okay, so we got started a little late, so I'm kind of on time, but we're almost out of time. The stress levels are surprisingly low. So this geodynamically, what this means is that we like to think of the plate at depth as being a kind of like rigid guide, but maybe that's not the case. And in fact, it might participate more in mantle convection, post-seismic processes than previously thought, and correspondingly is also not as an inhibitor to mantle convection as we would have thought. This is very related to what we think the mechanism of those earthquakes are. And what we can do is, if you have a mechanism for this weakening, we know that it must operate in a realm in which there are not large background driving shear stresses. So one common thing that we'll compare this with in the future is one idea is that you sort of get a localization of strain. So you're deforming the plate, but then it gets to a smaller and smaller zone, which then generates heat, which then lowers the viscosity, which then concentrates the strain more, which then lowers the viscosity. And so you get this sort of runaway weakening reaction happening. The problem being, all of these models require large background driving shear stresses. And so in the future work, though, we're going to try to explore the physics of what's making this observation more thoroughly. The other thing we didn't really talk about in this talk was anything to do with time dependence. We mostly focused on, let's focus on this upper left panel. This is the plunge of sigma 3 and sigma 1 against time. This kind of faint dashed line is the time of the magnitude 9 earthquake. So you see as we're cooking along, where compression is parallel to the down dip direction, the earthquake occurs, boom, we get a large change in the shift, and it slowly recovers back to the pre-earthquake levels, both sigma 1 and sigma 3, although we see very little, like much less in the lower plane, which is another constraint which we should interpret. The other thing I want to examine is, this was just in Japan. Is this something that's special about the Japanese subduction zone, or is this true everywhere? And so next we're going to go look in Chile. The problem, or what makes Chile more difficult, is they do not have nearly as many seismic stations. So I've been working with a postdoc developing sort of a machine learning method to pull out earthquake focal mechanisms. So it's just a lot harder and requires more work, but I think we can do a similar analysis in Chile. And then if it turns out that this is also true in Chile, the next step is to go to more broader global scale geodynamic models. I mean, what does this mean for the long-term effects on mantle convection and our implications for how we interpret running backwards in time? Okay, so having talked with people, I wanted to show a few slides really briefly because people were very excited about this new measurement which I've been working with called distributed acoustic sensing. And so what this allows you to do is turn fiber optic cables into basically seismometers, an array of seismometers. So what we've shown here offshore Japan is this is a fiber optic cable that was put in to receive data from offshore seismometers. So there's about 50 kilometers long of optic cable. This was after the Tokuoki earthquake was actually covered by sediments. And about 10 years later, they went and dug back and found the end of that fiber optic cable and plugged in this instrument, which shoots laser pulses down, and we were able to measure beautiful data. So what we're seeing here is this is a function of distance along the cable. And what you can see here, this is from a teleseismic earthquake. You can see this really clear arrival of an S wave all along the cable. And so what this can allow us to do is fix the problem I posed at the very beginning that sort of restricted us to only looking at intermediate depth earthquakes, because I wanted to be below the mainland where I had instrument coverage. So this is going to allow us to go to shallower depths further out with a similar quality of catalog. And the nice thing about this is it doesn't require huge millions of dollars of grant. It just requires you to plug in an instrument on the end of an existing telecommunications cable. Another exciting example of how sensitive this is, and really the value of having an array over one point. So this sort of red X here is one point, and so you can see there's a blip and that's a wave. Where did it come from? Where did it go? We don't know. Here's the spectrogram. But if you plot the entire cable, you can see that a plane wave came in like this. You can see it first arrived here and then later arrived here. And you kind of imagine that plane wave moving across the array, and you can see that move out across the entire instrument. Turns out what this is from a magnitude 4 earthquake in Chile. That's a tiny earthquake to be measuring 16,000 miles away, kilometers. But the reason you can do it is you have 10,000 different data channels to look at. And what's nice about this is that in addition to just looking at wave arrivals, this is in the Ridgecrest earthquake sequence. You can actually get really nice source information about each of these earthquakes. If you're interested more, I didn't talk about this today, but we have some papers going that I can send to you if you're interested in learning more. Since this was a job talk, I thought I'd give a little bit of what I wanted to teach. My primary interests are in seismology, geodynamics, and mathematical methods. And where I think I would fit in teaching is in geophysics, seismology. In particular with seismology, I'd really like to put a sort of what I would call an applied seismology, where we're trying to focusing on, I would provide notebooks on how you download data. How do you process that data? How do you use that data? Because that's largely what research and employers will want you to be able to do, in addition to just the theory. Geodynamics, I was thinking something along the lines of, for research students, both on an undergraduate level to be able to understand everything in the talk I presented today, and at a graduate level, be able to actually perform the research at a level of what I presented today. For I was thinking of natural hazards, in terms of my expertise is in earthquakes, somewhat in landslides and volcanoes. I think it's a natural extension to focusing on natural hazards. And I also think that one thing that's really lacking, and I think in a lot of current, at least, I'm a geophysicist, so I'm biased, obviously, but there's many mathematical methods, and you could kind of do a quick survey type course, so that even afterwards, you can't do it, you know that method exists and how to go find it and look for it and where to do it. And this is just kind of a fun example that I've used. looking at raspberry shakes, and in sort of in-class examples, you can do that. And that would be sort of an example of, we would then analyze that in our applied seismology class. All right, sorry, I'm a few minutes over, so I apologize, but thank you very much.
If you have questions, let's start with the students. If you have any questions,
Bring back the.
please. And I will say, if you don't want to ask him now, there is pizza in room 142. And Brent will be down there after this, and you can join and talk over our slides.
There were two specific points on your subducting plate.
Yeah.
How did you pick out those points as the stress points exactly?
So let's see here. So I didn't actually. That's sort of just a result of the way I plotted it to present, but let's. Oh, there. You guys saw that that's not what was supposed to happen, right? I think this is why. Okay. So what I really did is in this entire region, I calculated the stress. So this, in the red, I'm showing the compressive stress for my calculation. Blue would be sort of tensile. And I compared those stress changes with the values in this region, these regions. Now, I didn't explain this, but part of the reason I cut off my analysis here is because that's where I get a large change in my model. And then my sensitivity out here starts to become a little bit more sensitive to precisely which slip inversion I use. But that's a good question. Yeah, I don't pick one. I kind of use it as a representative area to represent what's happening in that whole region.
Gotcha.
I have a question about the fiber optic cables. So you mentioned that you just kind of plug something in at the end of one of these cables, but that you have like multiple points. So is it, when it comes to like measuring from these cables, is it you have just one device at the end of the cable or multiple?
So you have one device at the end of the cable. So what happens is, so what this device looks like is it's like, think of like a server rack, and there's two server racks where one is the device generating lasers, the other one is computers and storage. And you plug in the fiber optic cable to the top one. Then what that thing does is it shoots down really quickly at kilohertz laser pulses. Now the fiber optic cable is actually not perfect. It's not perfect glass. There's imperfections in it, and that causes scattering back. So what happens is now I've got a scatterer here, a little like defect in my cable that's sending back a scatterer, and one here. And I'm scattering from them quickly in time. And as that's happening, I'm able to measure the difference between these two scatterers in time. And so what you measure is at different points all along that cable, you get those sort of changes in length. Now, we plot these as one point, but what these really are integrated averages over a length, so what you call the gauge length. So if this was the cable, I'd take 10 meters of that cable, and for every scatterer on that 10 meters of cable, I'm going to measure the integrated phase change, and that's going to be my measurement of strain. So there's one device, but because the laser doesn't interact with itself forward and back, I can do that everywhere along the cable.
So do you see similar results in Chile and around the globe as what you did in Japan? You know, what would their theoretical implications for manifold convection be hypothesized to be?
So some estimates are that as I bend the plate, right, I'm actually eating up about 40% of the gravitational potential energy I gain from sinking of the plate into convection motion. So basically, you would have more convective motion than you would have previously thought going backwards in time, which would then change what you would expect the cooling history of the mantle to be, and consequently what you would then expect the cooling history of the outer core to be. And then consequently you might see very changes in your inferred strength of the magnetic field. So those are like the big ones that I'm sort of concerned with, but there would be other things which might be related to the sort of the style of convection. And the other place that this might be really interesting, and I don't want to speculate too heavily because I'm not a planetary person, but on a lot of other bodies we don't see subduction, right? And what might be something interesting is if we can pin down what the weakening mechanism is here, and if it's not present there, that can be a strong sort of supporter for why some of these other bodies may or may not have tectonic expressions like subduction. But that's very speculative.
Can I follow?
Yeah.
Why wouldn't the Wanda Fuca have enough instrumentation to answer?
So the Wanda Fuca could have enough instrumentation. The main problem with Cascadia, and it's really kind of the bane of most seismologists, is there are just no earthquakes. There's very little seismicity in the Cascadia subduction zone. The other thing for this study that is a problem is, well, at least for looking at the change in location of the neutral plane and both the stress inversion, I require a large earthquake happening elsewhere to perturb a stress field on top of it. And we don't have any record of the large earthquake. So maybe after the Cascadia subduction zone has a large rupture, we can do this again. But for now, we can look at Chile, which had a magnitude 8.8 in 2010. And we could look at Tokaoki, which was 2011, it was a 9.1. If we really, really want to push it, we could probably do Sumatra as well. But the problem there is you just have a string of islands with very sparse stations and noisy data. But a lot of really big earthquakes. Yeah.
All right. Thank you for the talk. It's really great. I just have one question. So, can the bending be your weakening mechanism here? Because as you can imagine, this huge slab, if you bend it, at least the very top of it, you would get fractures, basically.
So, yeah, I mean, I think that's a good idea. I think looking at the outer rise, what's going on in the outer rise, where your curvature is really high, is a good place to look for that weakening happening. The other piece of evidence for why that's a good place to look is our gravity observations, which is where you compare the topography and bathymetry to our gravity measurements, show that after the trench, most of the weakening has happened. Or at least the part of the elastic plate has happened. So there's a good evidence that maybe that a lot of that is happening in the outer rise, which would be where the bending is. But what the exact details of what that mechanism are, I don't know.
So the weakening you propose, you're saying is in the rise, outer rise, right? Somewhere before
I'm not. I'm saying it's a good place to look, I think.
One compositional reason that I know that might cause that is as you're having those faults and fractures and stuff, as the plate is bending, water can be infiltrated into the plate. Depending on how large those faults are, that could reach the mantle, forming serpentinization, which could certainly change the mechanical strength of the plate. I look for serpentinite within subducting slabs. And
Oh,
we
cool.
can find it from place to place, but it is harder to image. Like you said, you need really good coverage and really good data.
Yeah.
But if you were to put large-scale serpentinite slivers in between those faults, that would probably cause quite a bit of mechanical weakness.
Yeah. I mean, you can kind of think the bending moment here for a viscous plate, I think, goes like the thickness to the third power, right? So if you were able to cut up that plate and just mechanically disconnect the different segments, you're already going a long way to weakening the plate. The part that I need you to show me that the superpentanite is there, is that you can get it all the way down to here.
Park and Ride 2019. We can talk about it.
Yeah, sounds good.
Cool.
Yeah. Let's do it.
Carl?
Oh, I was gonna, I like that superpentanite idea.
Yeah.
So I was gonna actually add a couple other things. It seems to me that a lot of this is dependent upon the geometry of the subducting slab.
Yeah.
And so can't you model this in a number of places to see the effect of the rate of subduction or the speed of the plate to determine how much that is involved in the whole curvature and the bending and everything else? So I would see a lot of modeling before I'd worry about Chile or some other place to predict what you should see.
So, yeah, two things. One, people doing global surveys of different curvatures and plate subduction rates have shown that the curvature is like almost flat compared to plate rate, which is kind of surprising, and suggesting that rather than having the entire thickness matter, which is what would happen if you're sensitive to the plate rate, right? Because you can think of, as you get further away from there, the amount of extension you need to match that curvature increases. You don't see anything. So the argument is that actually something is weakening the entire plate, and actually most of these plates are deforming plastically, which all in these like yield stress envelopes. So observations show that the plate rate isn't strongly linked with the curvature. And I agree with the simulations. And at AGU, it's March, it's like 4 months ago, I was standing next to Magali Billen at UC Davis, who does these simulations, and we spend most of the time agreeing with you, and we're talking about how to actually do this.
The only other thing I would add on there is your time frame. So most of the changes you were looking at are very short order time.
Yeah.
If you look at the behavior of plate over millions of years, you see quite, in a Pacific plate,
Yeah.
for example, you see quite a variation in change in curvature and rate, and that may give something else. How much of this is instantaneous or something that's a long inherited pattern?
Yeah, that's why I think when I talk about that eta, I'm really talking about on the time scale where decay, the curvature with time, is approximately constant. So I'm really only talking on 10,000 years or shorter timescales, yeah. I can't say much about what's happening on millions of year timescales. And I can't really say if there's like hysteresis, if there's some leftover weakness from previous. And that's one of the main reasons I want to go then look at Chile. Because maybe it's something weird with the history of this plate, right? Maybe there's some reason that this plate is just damaged and weak, and the rest of the plates are actually strong. So that's why I want to go look at Chile next.
Did you check the chat quick just to make sure?
I can't, but if someone else
Go
can.
to my, yeah, just check the chat there real quick just to make sure.
Oh, up here? Oh, chat.
I don't think there was.
No, I think we're good.
Okay.
All right. Well, thank you again, Brent. And I don't know how much.